Welcome to the 2016 Alaska Fire Presentation Series. It is being brought to you by the Alaska Natural Resource and Outdoor Education Association, or ANRO. ANRO is dedicated to promoting and implementing excellence in natural resource, outdoor, and environmental education for all Alaskans. My name is Kathy Rezebek, and I would like to introduce our speaker today, Randi Jandt. Randi is a fire ecologist for the Alaska Fire Science Consortium. Today she will be talking about climate change implications for wildfire in Alaska. Welcome, Randi.
Hi, Kathy. I'm going to bring up my first slide there. The Alaska Fire Science Consortium is a knowledge exchange funded by Department of Interior agencies and the U.S. Forest Service, and in cooperation with all the organizations on the logos at the bottom there. And like Kathy said, I'm a fire ecologist working for the consortium located at University of Alaska Fairbanks International Arctic Research Center. And today, next slide, we'll be talking a little bit about the implications for climate on fire regime in Alaska. So perhaps nowhere are the impacts of recent climate warming being felt more rapidly or more dramatically than in the realm of wildland fire. Next slide. And that's the topic today. The management community, fire management community in Alaska really thinks that we are already seeing the intensification of wildfire that has been predicted to come with climate warming. And we're starting to wonder what new tools and strategies might be needed to cope with this in the next few decades if projections are correct. Next slide. So firefighting tools and techniques in the field haven't changed that much since the days of Rod Norham, shown here. He's often considered to be the father of Alaska fire behavior studies. In 1981, this picture was. But the environment, all these factors listed here, has changed fairly dramatically, with the possible exception of rainfall, which we'll talk about in a minute, thus changing the playing field for the fire management in Alaska. Next slide. The 2015 fire season in Alaska and Western Canada was a wake-up call to the kind of fire seasons that seem to be possible under the warmer climate. We thought 2004, shown in the red line here, it escalated quickly, but 2015 really left it behind. The week of June 19th alone, 295 new fires were ignited, and by the end of it all, about 70 homes were lost, 5.1 million acres burned, and we had fires all the way across the state, as you can see in the lower figure, all the way from the western part of the state to the Canadian border and the Brooks Range, all the way down to even a fire on Kodiak Island. We exported a lot of smoke across Canada and all the way to the Atlantic seaboard. Next slide. So research at UAF and at NOAA indicates that the changed climate is partly responsible for making fire seasons like 2015 possible. Alaska is warming twice as fast as the continental US. So from 1949 to 2014, as you can see in this graph of mean annual temperature departure, we've warmed about 3.5 degrees Fahrenheit during that period. And April through June of 2015 was the second warmest on record statewide. So this is year-round temperature, which is important, but next slide. But really, when we're talking about fire, the fire season is extremely sensitive to summer temperatures, and especially those very warm days. So this graph is showing what has happened to our summer temperatures, the maximum temperature in May through June over that same period through 2015. You can see there's been a steady increase in those maximum daily temperatures in Climate Division 3. That would be the interior portion of the state. You only really need a couple of weeks of warm, dry weather to dry out the feather moss fuel beds, like you see at the bottom of the screen there. Those fuels dry out rapidly, and once they dry enough to support fire spread, we can generate large fires. Next slide. So increased burn acreage has already been documented in Alaska, going along with those warmer temperatures. I started my field term in Alaska in about 1986, which is roughly where that blue triangle is at the bottom. And the thinking then was that big fire seasons came out at every 11 years, kind of like the sunspots. But the frequency of large fire seasons, if you define that as, say, over 1 million acres, has doubled since 1990, as you can see in this graph. And this isn't projection or prediction. This has already happened. You don't need to be a statistician to look and see what's happened to our fire seasons. Next slide. So what are we predicting for the future? Scientists at the Climate Research Center at UAF, including Dr. John Walsh, prepared this graph where they're looking at the 24-hour daily temperature. So that would be the average temperature over a whole 24-hour period. And they developed a model to work with climate projections to say how that will change over the next several decades. So the first box on the left is what we've seen already. So that would be from the 1971 to 2000. You can see that on average, we only have about 4 or 5 days. Their model generates 2.6 days, but reality is a little more than that. But still, only 4 or 5 days where the average 24-hour temperature exceeds 70 degrees Fahrenheit. But in the future, that's expected to double by mid-century and then double again by the end of the century. And we expect that this will have a large impact on fire danger indices. Most burning occurs on these extremely warm days. Next slide, please. Interestingly enough, too, the temperature trend seems to matter more than precipitation, which is a little counterintuitive. But as you can see here, and now I'm showing you Climate Division 3, it's that donkey-shaped thing in the middle of the state, pretty large area. So it was the 3rd warmest May and June on record, but only the 29th driest. So unremarkable from that perspective. What was a saver, really, is that we got that 2.5 inches of rain in the first week of July in 2015, which slowed the incredibly fast-growing fires we had at that time. And then we did get some snow in September. But those were fortuitous events. Next slide. So what about rainfall? Probably everyone's heard that the climate models for the future do indicate we'll be seeing modest increases in precipitation, although there's little confidence in the numbers. Well, and so far, none of those projections count for enough to offset the warming. But as you can see in that, again, the Climate Division 3 interior part of the state, our trend so far is pretty flat. We just haven't seen an increase in precipitation during the summer to go along with the amount of warming. And Mike Flanagan, a fire researcher at the University of Alberta, calculates that for every 1 degree of Celsius, or 1.8 degree Fahrenheit, of warming, you would have to have about a 15% increase in rainfall to offset and mitigate that moisture loss from the evaporative demand. And again, the climate projections don't really call for that much increased precipitation most of the state. Next slide, please. So that led us to this discussion. Dr. Scott Rupp, shown at the top there, a climate scientist and assistant director for International Arctic Research Center, showed this slide at the Alaska Interagency Fall Fire Review in October 2015. And we talked about, what would have happened if that rainfall in July hadn't come. We can see here the curve for fire growth for some different big fire years, including 2004 in the pink and 2015 in brown. So the thinking is that if we hadn't got that rainfall and the fires continued to grow exponentially like they did in 2004, we would have seen some very new level of fire activity. Next slide, please. So here are the lightning trends from large Alaska lightning data set that were analyzed by Farouk and Hayasaka. And notice that there seems to be an increase in the amount of lightning we're seeing as well, beginning in about the 2000s. Lightning is responsible for most of the acreage burned in Alaska, about 90%, although most of the fires are human caused. So in 2015, by the way, we would have been off the chart from this particular graph. Next slide, please. In 2015, we had one day in June had 15,000 strikes, and we saw 61,000 strikes in just 1 week during that period. So there's been some work on how lightning may change in the future. And Romps et al. Published a study in 2014 for the Western United States, which called for about a 12% increase in convective activity with every 1 degree Celsius increase in temperature. And it's likely that we will see that same magnitude or greater in Alaska. So we will have ignitions to go along with the warming. Next slide, please. We are seeing longer fire seasons. Alaska has more snow-free days. Breakup comes about 2 days earlier a decade, and snow, the permanent snow, comes about 2 to 5 days later per decade, based on satellite data. Some places have even more change, like for example in the Noatak in Northwest Alaska, the snow melt is actually 2 weeks earlier since 2000. So once the ground is snow-free, thawing and drying can begin. Next slide, please. Oh, and I should have mentioned that slide and this one. I'm showing you the first fire that was smoke jumpers went to in 2016, which was April 17th on the Nick River down by Palmer, a record for the earliest fire jumped in 65 years of smoke jumping in Alaska. So another way to measure fire season length is by growing season, and I'm just showing you here some data from the Bonanza Creek Long-Term Ecological Research Station showing how growing season has changed since the beginning of the century, and it has actually increased almost 30% in some parts of the state. Next slide. So if more fire is expected, how much is expected? Now, several different research teams have modeled this using different methods, but I guess one remarkable thing is that they all call for fairly substantial increases in fire activity. So this particular slide I'm showing you is some figures by Yui et al. From a team from Yale and Harvard, who used simple regression equations with large weather phenomenon like the 500 millibar height and max summer temperature, those types of things, to show how acreage burned might change with the climate projections that are favored for looking at future climate in Alaska. And so And just to show you that they got reasonably good fit on these equations, which are at a pretty coarse scale. So they're calling for about a 2.5 increase in burn area in interior boreal forest, and 4.8 times increase in what they're calling the boreal cordillera, which would include some of the more upland areas like Copper River Basin. And so that's a fairly substantial increase in fire activity. One big unknown I should mention is will there be fuel limitations that go along with this as we start to change the forest on the landscape? And we'll talk about that in a second. Next slide, please. Some research and a lot of expert observations support that fire behavior might be changing as well. So in 2015, for example, there were 4 advisories issued by the Alaskan Interagency Coordination Center for extremely dry fuels and the potential for extreme fire behavior. We did see explosive growth of some of the wildland-urban interface fires, and we have noted more and more that perhaps fires are burning into recently burned areas, a phenomenon that's sometimes called fire on fire. And over the past decades, we counted on those recent burn scars as basically natural barriers to new fire spread. We're not so sure we can count on them as much in the current climate. Next slide, please. So here's an example of that fire on fire phenomenon. So the Alaska Hotshots noted that they have seen fire re-entry into some burned areas like this, where they have what they call jackstrawed timber. So jackstrawed timber to me indicates that the previous fire was severe enough to burn out most of the organic matter and topple the trees. And that's what you're seeing in this slide here. It's rarer to have re-entry into these young stands, which have more deciduous growth. So ironically, a stand like this would have a greener signature on a satellite burn severity survey called Delta NBR, normalized burn ratio. And possibly because of that or other factors, the monitoring trends in burn severity work with the Forest Service, if you're familiar with that, has not yet picked up on a trend for increased fire in Alaska. But it's not tailored ideally either for boreal forest conditions. It was kind of developed for the dry coniferous West. Next slide, please. So another way to ask about fire re-entry in the burned areas is to ask whether fire return intervals are getting shorter. And Jennifer Barnes with the National Park Service, she's a regional fire ecologist, did a nice webinar that's available on the Alaska Fire Science Consortium Vimeo site if you want to see how she's getting data from the National Park Service's burn monitored fire plots to gather field evidence on that question. The Fish and Wildlife Service Western Region FMO also noted that they thought they were seeing more reburns in recently burned areas and an earlier start to fire season. So there seems to be multiple lines of evidence here, field, expert observation, and modeling pointing to these types of changes. Next slide, please. So given that we seem to be seeing a change in the fire regime and more frequent fire, are the forests changing as well? So this is a figure from a 2001 paper by Dan Mann, who discovered, using satellite data and also an extensive inventory of tree cookies that had been collected across the big swath of interior Alaska, to model the ratio of coniferous to deciduous trees, spruce basically to hardwood forest, and what that mix had looked like over the past several hundred years, and found that it had been through time, for a long time, about 2/3 coniferous to 1/3 deciduous, as you can see in that back cast. But then it seemed like right in the last few decades that ratio started to dive. And so they had an opportunity to have a snapshot in 2001 with a satellite data set that covered the entire state, where they could look and see what one vegetation scheme said about that ratio. And there it was in 2001. So this is really interesting. If this major change in vegetation cover was happening right under our noses, and I was really curious. So I asked some folks at SNAP if there was another snapshot available more recently, and they found one from 2005. Next slide, please. And this hasn't been published yet, I might add, but the next snapshot they found in 2005 indicates that this trend is ongoing, not surprising after the big fire seasons of 2004 and 2005. So a fairly big shift in forest cover species maybe is occurring with this change in fire regime. Next slide. Let's talk a little bit about ice now. Why would we care about ice when we're talking about fire? Well, fire is affected by ice in the ground and vice versa. So in much of interior Alaska, we have it's a very dry climate. And without that ice in the ground to hold the moisture near the surface for vegetation to grow, we would see a more desert-like and a more well-drained landscape. So permafrost affects the vegetation, which affects fire, and then fire in turn affects vegetation. So first of all, what is permafrost? It's defined as ground or soil and rock, included ice and organic matter that remains below freezing for at least 2 consecutive years. And the thickness varies a lot from north to south in the state. It could be less than 1 meter thick to 1,500 meters thick up in the northern part of the state. And a lot of it formed during cold glacial periods, and it's persisted through more contemporary warmer periods in the last 10,000 years. Next slide. And this is just to show you kind of where it is. You may have seen this type of thing before, but to show you that much of the state has some effect from permafrost. So, next slide, please. Now, what you might not know is how vulnerable that permafrost is under a warming climate. So this is, I'm sorry if this graph is kind of small, but it shows you a trend in permafrost temperatures being monitored at 1 meter deep. So 3 feet under the surface, the permafrost is doing this. And everything to the left of that blue line, that blue vertical line, that's already happened. That is how much permafrost at various places, Barrow in blue to Fairbanks in green, Gacona in the black there. It's remarkable, really, that permafrost at that depth is increasing that rapidly in temperature, to me, especially up north in Barrow and Happy Valley. And then the projections with warming climate in the future show, as you can see, the permafrost temperature in some of those areas, like Fairbanks and Gacona, rises pretty quickly above 0. Therefore, what they're saying is it's going to thaw. Next slide. And that will have a real impact on drainage and drying, and it's going to have an impact on fire issue. So let's talk about how fire, in turn, can have a feedback effect on the ice. This is a recent study by Bruce Minsley and his team, looking at the Rosie Creek burn, which happened in 1983 south of Fairbanks, and that and it's using a series of thermocouples a grid to look at temperature, subsurface temperatures, and map basically what the permafrost is doing. So the LTRB, that would be the Rosier Creek burn area on the left, still shows a fairly significant degree of thaw at depth there. As you can see, those are meters on the left, so down 10 meters or so. It's still showing significant thaw compared to the unburned area over on the far right, which is still frozen. And then the fire line, which is the LTRF in the middle, that has also significantly thawed and pushed a bulb of thawed soil even under the unburned area. One interesting thing about this particular study is that they noted that if the remnant organic areas are one of the things that help insulate and protect the permafrost, and if those remnant layers after fire or some other disturbance were greater than 13 centimeters, that was much more likely to protect the permafrost from dramatic melting. Next slide. So here's one more example of how fire can have effect on the permafrost and how in turn that affects the landscape. This is from the North Slope fire in 2007 and Iqtuviq River fire, which was a very severe, i.e. deep burning fire. And Ben Jones from the USGS used a LIDAR method to show you the surface pattern of permafrost in the burned area after the fire. And so you can see how it progressed from kind of a smooth looking surface to a very roughened surface where it's polygonated, and the trenches, the channels between the polygons have thawed down to about 1 meter in depth, and the whole landscape has subsided to about 0.2 meters, which is the blue color there, in the burned area. So fairly dramatic landscape changes following this severe fire. Next slide. So I have to mention a little bit about carbon banking because it's been a subject of interest recently. Basically, the forest is a very, and the tundra, they're very important ways to bank carbon that store a lot of carbon. And normally one would think that Alaska would be a giant carbon sink where a lot of carbon can be stored in all of our organic material and the tundra and slow decomposition and extensive forests. However, the recent changes in burning in the fire regime are starting to change that equation. So the Bonanza Creek long-term ecological research folks found that interior Alaska may have lost some carbon stocks in the boreal forest area between 1950 and 2010 due to that increase in burning, up to about 3.4%. And there's some concern that with further increases in burning, Alaska could become more of a carbon source than a carbon sink. Next slide. That would in turn feed back to the processes that are already in place, warming the atmosphere. And of course, that's the concern. So for example, the 2015 fires alone released, do you see that in the top of the slide that's circled there? 59 plus or minus teragrams of carbon emission from those, all the acres burned, the 5.1 million acres that burned in Alaska in 2015. And it's a Boreal-wide phenomenon. So in Northwest Territories, when they had a record fire season in 2014, they released almost 3 times that much, 157 teragrams of carbon. And so that's a lot of years of carbon deposition. Next slide. So, keeping the carbon in banks, it keeps it from accelerating the rate of warming. And then there's also the wider implications of emissions. And so this little graph here is from Fire on Earth, a online book that is free and available and has some very interesting information in it. And I picked that to show this shows the carbon monoxide plume from the Alaska fires of 2004, our record fire season. And you can see that red plume goes all the way across Canada and to the Atlantic seaboard. And it's remarkable that in 2015, almost the same pattern emerged. On July 2nd, weather.com posted that the northwest winds aloft transported the smoke plumes from Alaska and Canada large fires all the way to the Atlantic seaboard, producing a hazy moon as far south as Atlanta, and smoke over in the mid-Mississippi Valley, in the Tennessee Valley, and the Appalachians. So increased boreal burning is going to affect areas not just in the Northlands. Next slide. And there may be some very specific impacts of this increased burning for air quality. So the Yui et al. Study I referred to earlier, 2015, Harvard and Yale, looked at how that increased burning they modeled might impact air quality. And they found that, for example, with ozone, it's generally less than 40 parts per billion volume now in Alaska, and about a quarter of that might be from boreal wildfires. The changes we would probably see due to wildfire, projections are correct, might contribute an additional 5 parts per billion volume, or actually on those really smokiest days, up to 15. And if you're wondering what is the threshold that's of concern for health, at the bottom there you can see that EPA has an 8-hour standard now of 70 parts per billion volume, but they're considering lowering to 65. Of course, when you have large wildfires covering the state, you can't limit exposure to 8 hours. Although there are some strategies that are being developed to sort of mitigate exposure to vulnerable populations. But last year, some villages, including Tanana, were evacuated due to smoke concerns. So this is ozone. Next slide, I'll show you some work from a Yale graduate student. Go ahead and bring up the next slide there. Lucia Wu is doing a master's study, and notice that this data is preliminary up there, but she gave a webinar and showed us her projections for increase in particulate matter, 2.5 microns, which, as you will recall, are the smallest particles that penetrate deeply into the alveoli of the lungs. And so they're one of the emissions of concern. And she thinks with the projections, using again the projections that Yui et al. Came up with for increases in burning, that most of Alaska will be exposed to twice as much PM 2.5 in July and August by mid-century. Notice this is by mid-century, which is not that far away relative to the control period. And some parts of the state will see dramatically increased PM 2.5 exposure, like look at eastern interior there, where the levels may rise by as much as 300%. North Slope also looks much higher in July, but recall that right now we have very little fire in the North Slope, so that's kind of going from a 0 to some effect. Although this data is preliminary, it does give you a feeling for the magnitude of a potential human health impact. Next slide. And then there's the whole issue of habitat and wildlife and the federal agencies' mandates to protect and nurture these resources. For example, Gustine et al. Had a study out recently and predicted that caribou herds would see reductions in lichen-producing habitats like the one I'm showing you in this picture. Lichen like this is called, some people call it reindeer moss. Lichen is a old growth species And this lichen stand like this could be, 100 years old. It's very sensitive to fire, and it regrows very, very slowly. So Gustine et al. Predicted this would at a minimum alter the distribution of caribou, and it might also impact the subsistence harvest opportunities for rural communities. Next slide. So given this science, it all sounds, fairly alarming. And how can we use any of this data to guide fire management and land management policy? So I'd like you to think now a little bit like a manager, like some of the agencies that are in charge of dealing with protecting communities from fire and protecting natural resources. Next slide. At that same meeting in the fall where Scott Rupp showed the hypothetical big fire season, Dean Brown from the state of Alaska said, the operational options are still much the same with a few more toys and a lot more data. I love that statement. Agencies are dealing with all these day-to-day realities that I'm not going to read to you. You can read in the yellow. But basically, how do agencies manage more exposure with the same resources? Next slide. For example, the state spent $180 million on fire suppression in 2015. That's about the same as the whole budget for the Department of Natural Resources, and that clearly is not sustainable over the long term. The Fed spent about the same amount, and the state is facing reductions of maybe as much as 16% to the forestry budget over the next 2 years because of our economic situation with declining oil revenues. At the same time, the costs for planes, helicopters, fuel, wages, all those things go up every year. So how are we going to deal with this? And this runaway, quote, fire season scenario, I guess now we are thinking we can imagine this, but we need a way to deal with it. How are we going to be ready? Next slide. So there was some operational brainstorming, and I want to caution you that what I have on this slide is exactly that, raw brainstorming as to, what the managers are thinking about that they might do, because, we want to do something. We are self-sufficient in Alaska. We are can-do, and we need to come up with some ways to deal with this situation. Next slide. So one of the things that, of course, we think about right away is fuel treatments, and it's certainly likely to be one of the major adaptation strategies that agencies hope to use. These photos are an example from fuel treatments that were experimental fuel treatments of thinning in black spruce that were challenged by fire during the Nenana Ridge prescribed burn, and there's a nice write-up on that, and actually a web page that you can access a lot of data and examples and photos from at our website, at the Alaska Fire Science Consortium website. But basically, the bottom line for that particular treatment is, as after the treatment, which you can see the treatment area on the right, a lot of grass came in after those spruce trees were thinned out. But the grass actually had a higher fuel moisture in the peak of fire season, like June, July. And as you can see, the fire didn't push as far into that moisture-laden live fuel as it did into the unthinned area. Next slide. So this slide is from Lisa Saperstein with the Fish and Wildlife Service, just showing how the Funny River fuel break around Soldotna really helped during the Funny River fire, and probably saved about $250 million in property damage is the estimate. And so certainly Fuel treatments and fuel breaks are one of the strategies we will be thinking about. Next slide. There are several new papers out looking at the effectiveness of some of these fuel treatments, including the Nenana Ridge and the Funny River fire. And there's a study in progress now, sponsored by the Joint Fire Science Program, looking at the effectiveness and the potential cost offsets for suppression. By having fuel treatments in place beforehand, one might use different strategies in suppressing fire, and that might reduce the costs and the number of resources that are needed to deal with a fire, especially at the urban interface. Next slide. So is there a role for science and technology in helping us out with our future fire problem? These are just some examples where some rubber meets the road, I guess you might say, with the development of science and technology. So satellite detection of fires has become a tactic that we're using in the last 15 years or so that's working really well for managers. And there's new satellites going up all the time. I heard recently a figure that there's just from the United States, there's about 1,600 satellites of various sizes up there now. And so there's a lot of new technology we might tap into. Infrared mapping capability has advanced, and of course, communication technology is advancing dramatically. There have been improvements in some of our weather models and our risk forecasts. And for the first time, in 2015, Alaska had a smoke dispersion model to use, and that was a very key tool to use in deciding when and where to do some evacuations for potential smoke exposure. And we are starting to have some work on understanding the factors and modeling leading to extreme events. So, like seasonal forecast predictions. So all these things, there have been advances, and there are areas of active study. Next slide. Now here's a wish list that I put together just based on some discussions with agency folks, but basically the fire protection agencies in Alaska, which include mainly the Bureau of Land Management, Alaska Fire Service, the state of Alaska, and the U.S. Forest Service to some extent in southern Alaska. They are especially interested in changes in the fire weather indices that are projected for the future, in better prediction tools, and in real-time ability to track those fuel moisture trends that determine whether we can get burning into the deep organic layers. Meanwhile, the land managers and wildlife managers, all those agencies in the state that are concerned with managing the federal lands, the state lands, and the fish and wildlife, they are especially interested in documenting the trends in fire severity and the resultant impacts on permafrost and on vegetation. And both of these groups would like to quantify the potential effects, if any, on changes that they can make to fire management policy. So I guess the next slide, as we're winding down here, I just want to mention that with respect to the wish list, we've had some recent success with proposal funding just this spring in 2016, over $1 million of research money coming in and recruiting some real talent to look into some of the critical questions that managers are interested in preparing for the fire regime of the future. And so I guess next slide, if I had to sum this all up in one sentence, this would be it. In Alaska, the fire agencies are looking to fuels management, mitigation, along with more exacting forecast and fire behavior models to offset greater service demand with flat budgets. And I'm going to close out here. Next slide, please. Just remind you that for more information on any of these topics that I've touched on, you could go to our website in the gold box there at akfireconsortium.uaf.edu, and we have a lot of resources, including publication access via the Alaska Reference Database, and webinars at our Vimeo site, and a lot of other resources to connect with more information on those specific topics. And I thank you for listening today. And I guess we will close out this webinar.